In a very old joke, a group of people take turns trying to say the largest possible number. Of course, the last person in the series will win by simply saying, the previous number plus 1. In fact, the sequence of numbers is infinite, and therefore there is no largest number. In reality, even infinity in mathematics is more complex than one might think, in the sense that there are different types of infinity, and numbers that, despite being infinite, are different from each other. Consider, for example, numbers composed exclusively of 2 and 3, 22 and 33, 222 and 333, 22, 22 and 33, 33. In all these cases, the second is always greater than the first no matter how many digits we add. We therefore expect that this property will somehow hold even in the limit where we add infinite digits to both. Before trying to answer the previous question, let's consider the following problem. What is the largest number in the interval 0 to 1? Obviously the answer is 1, but what if we excluded the extreme? We can progressively approach unity by considering decimals that contain an ever-increasing number of nines after the decimal point, for example 0.9, 0.99, 0.999, etc. In this way, if we tried to continue the sequence infinitely, we would get closer and closer to unity. Numbers with infinitely many digits after the decimal point can be divided into two distinct categories. Recurring numbers, where a sequence of digits of finite length is repeated infinitely, such as 0.123123123. And numbers where the sequence has no regularity, such as in the case of the number pi. The former are called rational numbers and can always be written as a fraction. For example, the number 0.3333. With infinitely many threes after the decimal point, can be written in the form 1/3. The seconds, like pi or square root of 2, conversely, are called irrational. Returning now to the initial problem of the largest number in the interval 0 to 1, what number would be greater than the one consisting of 0 followed by infinitely many nines? 0.9999. In fact, it's easy to verify that this number coincides with unity. Consider the following sums. It's clear that if we increase the number of nines indefinitely, the second term of the sum will tend to 0, and therefore in the limit the first term tends to unity. This result can also be obtained in the following way. Recall that if the modulus of x is less than 1, we have we can write the periodic number 0.9 as the following sum. On the other hand, if we apply the previous equation, we have, as expected, we have the result that the periodic number 0.9 is equal to unity. Let's try now to extend the previous considerations to the entire range of numbers, up to infinity. Consider a hypothetical operator that reflects all the digits to its right with respect to 0. For example, the number 0.123 would be transformed into the number 321, the number 0.99333 into the number 33,399, and so on. In this way we can imagine an infinite leftward limit. By reflecting the periodic number 0.3, we obtain in the limit an infinite number, made up of infinite threes. Therefore, if we wanted to find the largest number of all, we could consider the limit of the number with infinite nines, which we abbreviate to periodic 9. Note that the presence of the 9 is linked to the choice of the decimal system, where 9 is the largest digit. In the binary system, for example, the largest digit is 1, and the largest number would look like a string of infinite ones, while in the hexadecimal system, where the largest digit is indicated by f, the string would have the form FFFFF. The following considerations do not depend on the choice of the numeral system, so we can return to the decimal system. Let's consider now the following sums. In the limit where we add infinitely many nines to the left of the first term, the term on the right of the equation will tend to a number composed of infinitely many zeros, with the 1 on the left never arriving. In other words, in the leftward limit of infinite nines, the term on the right tends to 0. We can therefore formally write that periodical 9 plus 1 is equal to 0. Paradoxically, what seemed to be the biggest number tends towards the negative number -1. This result can also be obtained in the following way, using the following equation again. We have said that this expression is correct if the modulus of x is less than 1. In the context of complex numbers, it is possible to extend this result with what is called analytic continuation. We note that the expression periodic 9 can be written in the form whose value is clearly infinite. If we try to use the previous formula anyway, we get That is exactly the same result as before. This implies that periodical 9 is equal to -1. It is possible, however, to construct an even larger number than this, by adding further digits after the decimal point, for example by considering periodic 9.9, or periodic 9.99 up to periodic 9. Periodic 9. The result should be periodic 9, plus periodic 0.9, equal to -1 plus 1, i.e. 0. The largest number of all, therefore, turns out paradoxically to be 0.